Let's start the next session. It's my pleasure to invite the first speaker, Yuri Kudenko, who is going to tell us something interesting about accelerator neutrinos.
Thank you very much. Yeah, thank you. So just I would like to thank organizers for inviting me to give a talk, such a talk. Basic scheme of a long baseline neutrino oscillation experiment looks like here. So decay volume, of course, target were produced pions and kaons, then near detector and far detector at long distance. Near detector close to the target or decay volume. So what is main task for near detectors? Of course, control beam direction, measurement of neutrino spectra before oscillation. That is important because here, when you study oscillation, we need long baseline, and then measurement of neutrino components, contamination, and some mixture of different type of neutrinos, and then measurement, of course, of neutrino cross section. This is a main task, but on the other hand, we also can study a lot of physics and mainly beyond of standard model. Just I cannot say for free, but this detector can study this physics as a byproduct. So let me concentrate on this hidden sector of beyond standard model. So it's very popular approach, dark sector and standard model connect through so-called portals, and possible portals interactions. It's vector, it's a dark photon Z prime, milli charged particles. Then neutrino portal with heavy neutral leptons or heavy neutrinos. Then scalar, dark Higgs, and pseudoscalar axion-like particles. And also very important, of course, light sterile neutrino. Of course, they not in these portals, and predictions for them not, I would say, so clear. It's just experimental hints, so just show you. And I would like to mention here that photon, dark photon, and Z prime interchangeable. So they so close, and sometimes you can say dark photon, sometimes you can say it's just Z prime. Okay, let me slightly apply picture for this non-standard particles. So sterile neutrino already a lot of told about that. So there are three anomalies, so-called LSND mini-Boone anomaly, which shows some oscillation with a mass about delta m squared 1 electron volt square. Then gallium anomaly, already mentioned several times, and so-called reactor anomaly. So all these anomalies, more or less, I would say, at some level consistent, and they hint on existence on fourth neutrino above this standard picture. Say, assuming normal ordering, we could add fourth neutrino, so-called sterile neutrino, with mass about 1, close to 1 electron volt at this level. Then this standard PMNS matrix can be modified, adding this connection with sterile neutrinos. You cannot detect sterile neutrinos, but they can mix with our standard neutrinos using this expression shown here. This is light. Then about dark photon, of course, vector portal, and this standard Lagrangian can be extended, adding this massive fields and this mass of photon m, and also this mixing parameter epsilon. So how can they produce? They can produce from pseudoscalars using these decays, and also it's a mass less than 0.4 GeV, and also important, they can be produced using this mechanism proton-Bremse-Strahlung. When you see this vector dominant model, you see some serious, very significant resonance at the level of about 0.8 GeV mass of, for example, raw meson. This is a main mechanism for accelerator experiments for production of such particles. Then about milli-charged particles, they introduced quite long time ago in paper by Okun. And why they important? Because they can violate quantization charge. Then they can be part of dark matter, so-called milli-charged dark matter. And then dark photons can connect to milli-charged particles, and important limit then dark photons have almost very small or even zero mass, and of course some extra dimensions. So of course, this if they exist, they can provide coupling between ordinary photon and dark sector. That's also important part of this portal. And finally, heavy neutral leptons, most popular so-called neutrino minimal standard model developed by Mikhail Shaposhnikov and colleagues. So it assumes that in addition to standard model, there are free neutral, in Russian, neutral heavy leptons or right leptons. So and mixing parameterized using these theta parameters, it is very small, level 10 to -5 for this mass of n or NHL, mass of NHL, level of GeV, and neutrino mass 0.1 GeV. So then branching to discover this particle proportional to theta squared, and basic, or I would most popular part of this model, or I would say phase of this model, predicts existence of one very small mass, less than 100 keV, and two HNL with a mass of GeV. So what instruments we have to detect? One is T2K experiment, which is running. And it has, of course, production, target, decay volume, and here is a lot of near detectors. That is important. And far detector is super Kamiokande. So near detector complex shown here. And it has very interesting features. It has quite heavy mass colorimeters and pi-zero detector, low mass tracking detector, and extremely low mass TPC chambers filled with argon gas. So you mostly neutrino detect interacting in this pod or in this fine grain detectors, plastic scintillator, and then using this TPC track of these charged particles reconstructed. Important, again, very important that there are some elements with low mass, exactly time projection chambers. And then this detector will be upgraded and used in Hyper-K experiment. It's shown here. This pod will be replaced by additional time projection chambers and very segmented super FGD, super fine grain detector, which has about 2 million scintillator cubes, and show it here now. It's a stage of assembly and preparation for beam. Another experiment which is running, it's NOVA in the United States, also use this off-axis neutrino beam and near and far detector. And near detector is just active, fully active, segmented scintillator detectors. So it's a good tracking, but there is no low mass. It's good to reconstruct charge tracks, but additional problem maybe with neutrino interaction. Then next project I should mention, because looking for future, is new experiment under construction, so-called DUNE experiment, long baseline neutrino facility in DUNE at Fermilab. And far detector will be liquid argon scintillator, but we are interested in this near detector complex, which also under construction. And it has now liquid argon TPC, then muon detector, and this so-called sand on axis, which consists of drift tubes, so more or less low density detector. In future, also probably will be installed here gas pressure argon TPC, pressure TPC. And final project, Hypercommand, also under construction from 21 and expected to start in 27. And it's a far detector with huge program, and also near detector will be used for this experiment, because main goal of this experiment, of course, search for CP violation and study of neutrino oscillations. And so I already mentioned this upgraded near detector, and also will be built intermediate water Cherenkov detector. So now we have such instruments, some of them running, some of them will be constructed, and results already obtained, and what we can expect. Sterile neutrinos. I start from sterile neutrinos. T2K experiment use very interesting approach. You know, we use muon neutrino beam and muon anti-neutrino, and we have only about 1% of neutrino, electron neutrino flux. But still very useful to use this, I would say, low contamination, but still high intensity flux. And for normalization, we use muon neutrinos. And then this approach, very interesting, and this exclusion plot with Patox already excluded for sterile neutrino, and shown here with some other results, and also here neutrino 4. And result was published quite long time ago, so about 8 years ago. Now we continue analysis and expect to extend this exclusion area. So it's an interesting approach just to use not this detector as byproduct, but also use this admixture of electron neutrinos, which very bad for study of new muon to new oscillation, important for CP search, very useful for study sterile neutrino. Then very interesting result obtained in Minus detector. I didn't mention because experiment is finished. So this result, new mu disappearance, and this is a combination of Minus, Diabe, and Bouget. Of course, all this experiment disappearance reactor, Diabe and Bouget, and Minus also disappearance, but accelerated. Here, muons disappearance, there's electron neutrinos disappearance. So this is exclusion area. They completely, well, of course, it's 90% confidence level, 99 still slightly not completely covers with LSND mini-Boone effect. But again, it's not direct exclusion. And then, of course, NOVA also provided some result. But if you, at the moment, compare with Minus, for example, with green, still they cannot reach such sensitivity. But NOVA is running, and I hope in future they improve this result. Then DUNA. DUNA is coming. I hope it will start in 21. Extremely sensitive. You see here all this, including LSND, mini-Boone, and all these anomalies here. This is sensitivity. Assuming no systematics. Excellent, fantastic sensitivity. But only if you assume 2%, systematic at level 2%, degradation of this sensitivity is almost 2 orders. If only 5%, it will be here and probably cannot even completely cover a problem of existing anomalies. You know how, it just exactly shows how important this systematics, because you collect a lot of events near detect, but then systematics getting more and more serious, and background and systematics really dominating factors that can kill your sensitivity. Then about dark photons. T2K and DUNA. T2K is doing analysis, and it is just expected sensitivity. It's not result. I just show some estimations. So it will be interesting, not showing here, this is black. These gray areas already excluded. So probably T2K will reach interesting sensitivity here around this vector dominant resonance 0.8 GeV. But together with Dune and continuing data taken for in time of hyper K, you see here is sensitivity of this Dune and hyper K. And okay, thank you. And you see it's quite interesting, even some proposed experiments designed to search for this, not only for dark photons, it's comparable with two projects just making this search as byproduct. Is very exciting. Then I already mentioned dark photon and Z prime, very interesting idea to use a heavy target here in T2K with spot, which will be removed, but now we have a lot of data. So process of interaction of this muon or what a mixture of neutrinos with target, with lead, because a lot of lead here. Then you produce a heavy neutral lepton, and through this mechanism Z prime, and then again mixture, and then Z prime decays into E plus and minus. Of course, many processes can do the same, but this idea of using interaction here might help to distinguish between different models and say dark photons or Z prime, et cetera. And interesting idea. And again, important to use low density and decay of this heavy lepton inside gas. Background is seriously suppressed, and sensitivity, and show it here, is quite impressive sensitivity. Just in this case, it's maybe several times better than existing limits. And then milli-charged particles. So they can be produced from raw omega 3 decays, like this way, or using this decays of pi 0 eta prime, and branching show it here. So two different mechanisms. And idea to use, again, segmented detector. Already this approach used in argon detector. And after upgrade of near detector of T2K, where will be very highly segmented new detector, milli-charged particles can interact twice, distance about 2 meters, interact twice. And this estimation showed that quite serious sensitivity can be attained using this approach, and background suppression will be extremely good because you reconstruct direction to just pion production target, and suppression of background very significant in this case. So you see here this argonute result, and this is T2K and T2K and in time of hyper K, very good sensitivity here. And if you look even here, T2K here, and dedicated experiment at about the same level. Dedicated, I mean, not yet even running because they proposed. And then search for heavy leptons. The idea to use these low density elements, and this already done, and results obtained in here in T2K. Most interesting is the mixing of heavy neutrino with tau neutrino, just improved more than factor 10 with previous result. And here also results were improved. And what is important, even now, you see here results from T2K, still the best. And if you look in future, here is T2K, and here all proposed new experiments. T2K means T2 to K during era of hyper K. Even here is high phase ship shadows at CERN. And still this result will be, I would say, very competitive, even better. And you see here all elements. You see T2K and Duna here, better than proposed experiments in this mixing with muons. And here is Duna, T2K not shown, only maybe ship not approved will be better. And here again, these experiments showed very good performance. So let me conclude. Just very rich beyond standard mode physics with new detector. And I mentioned vector and neutrino portals, this result. And of course, light stereo will be also open. Thank you very much. Thank you very much.
Thank you very much for your presentation. I would like to ask you, when you are speaking in your review part of your talk on new physics, you mentioned the milli-charged particles. Are effects of milli-charged neutrinos itself included?
You know, yeah, in this case, yeah, I understand your question, but in this case, just models we used for estimation. Yeah, so we, of course, we didn't, to be, I would say, we didn't consider mirror charge of neutrinos here. But yeah, I know that some effect or also can be studied of milli-charged neutrinos using these detectors. But yeah, I know. Yeah, I know that they exist. Yeah, I exist. Yeah, I agree. Yeah.
Excuse me. The question, you've shown a lot of plots which are related, maybe through the previous and future talks, to searches of the dark matter and still neutrinos. I'll ask the question concerning dark matter. Are the values of the parameters which are studied in these experiments you are describing are compatible and intersecting with the values of the dark matter parameters and, for example, dark photon parameters, which are considered by the NA experiment by the colleagues from INR and CERN?
You mean what experiment?
NA.
A64.
Absolutely.
Right. I think, I didn't show here the plot for example, if we look at dark photon, NA now provides a better than, for example, T2K sensitivity. But in future, I'm at this level, we don't know. Of course, we have to compare projection of NA64, and we don't know about future, to be honest. And projection here. So it will be at, I would say, comparable level. If NA64 will continue, we know for sure that hyper K will run. Yeah, it's definite. Yeah, but NA64, I don't know. Anyway, at the moment, NA64 better, but for future, I don't. Yeah, thank you.
Let me invite the second speaker, Dr. Drachnev, who is gonna tell us what happened in Borexino. Please.
Thank you. I'd like to thank the organizers for an opportunity to speak here and to bring one of the remaining part of the past Boraxino glory, since the detector is already decommissioned, but the data is still there, and there's something to dig out. Something's possible to dig out. So Boraxino is still quite a large collaboration, including more than 100 people from mostly Europe, Russia, but United States as well. So, well, that's the short outline of what I'm going to speak about. Oh, well, we are going to speak about Boraxino, and for the Boraxino, although it did a lot of side jobs, the main purpose was, of course, always the solar neutrino. And the sun, as we know, is quite a powerful source of neutrinos since it's powered by thermonuclear reactions. And there are two reactions that are there. There's the PP chain, which is, as for the sun, the dominating one. It's like 99% of energy is produced through the PP chain. But as for the universe, in larger stars, the most important reaction is the CNO cycle. Of course, this is not the only scheme. There are various schemes depending upon temperature. This is probably for the cooler stars that do run the CNO for the sun as well. Of course, there are some other versions. So the CNO is another source of energy, and it's important just for the universe, at least to see whether it exists for real, just directly. And Boraxino can do it. So this is just the famous picture by John Bacall in 1995, if I remember correctly, for the solar neutrino spectrum. Here, so here you see all the monogenetic lines and continuous spectra for the PP and the CNO. And another purpose to search for the CNO, to measure the solar neutrinos, is the problem of solar neutrino models, because there are two classes of solar neutrino models. Sorry, not neutrino, sorry, solar standard solar models like GS98 and AGS09, so high metallicity and low metallicity. And they differ actually by the ratio of beryllium-7 boron-8 that just depend upon temperature. Of course, also the sound speed profile differs, and just directly by the CNO, by the metallicity. So the presence of elements heavier than carbon in the sun that are actually active in the CNO cycle. So this is something very direct, and measuring the CNO defines the metallicity. So, well, we were using the Boraxino, which was located in the one of the world's largest underground laboratories under the Gran Sasso Mountain, just in the Terma between L'Aquila and just in the tunnel between L'Aquila and Terma in the whole sea. Here you see the picture of the detector already, since it was insulated in 2014, and on to stabilize the temperature of the detector. And this is a construction of it. It uses the concept of graded shielding. So outside we have a stainless steel tank that contains 4,800 tons of ultra pure water, and then inside, in a stainless steel sphere, we have this insulator, which is the pseudocumene, with a quencher outside. And in the innermost volume, which is the volumes are separated by very thin nylon, average thickness 125 micrometers. And inside we have the insulator with the wavelength shifter that makes the Bragg shift, so makes the light, makes this insulation light that is that the PMTs are sensitive for. And inside we have around 2,200 PMTs that are watching this volume. So this is how it looks in real life. It's actually a CCD camera picture. Boraxino, what's the main feature? The main feature is, of course, the radio purity. As for this insulator, it's something unique. We have suppressed all the radioactive contaminations by enormous factors. Even for carbon-14, it's 10 to 8, just the selection of the right tool. For others, it's up to 10 to 12 with respect to normal radioactivity. So this is how the spectrum actually looks. It's more or less for phase 1, so it's not even the cleanest Boraxino. It's just a simulated data. So this is just the list of components that we're considering in our analysis. Then, well, some of the components can be suppressed with some features. I'm not listing all of them, but this is, for example, the carbon-11, then can be suppressed by a veto because it's produced by spallation. So you have the muon, I have the neutron. You can put a geometrical and temporal veto and separate the data set into two parts and feed them independently. So in one of them, you suppress carbon-11 by 92.4% for some lifetime loss. Plus, we have also the likelihood of the position reconstruction, of the top position reconstruction. That is also different for positron because there are two gammas in most cases, and the geometry of it is a bit different. So it's not as point-like, it's just an electron. And so this is a way of suppressing carbon-11, which is in the CNO region, actually. So it is something that is important. The CNO has a spectral shape is very similar to bismuth. So there was a large work done for the bismuth 210. So we were tracking the polonium that can be discriminated with the MLP. So quite reliably, it's an alpha. It has a different scintillation profile that just the scintillation flash is has much longer duration. And this is how it looks, the polonium map. This is within quite a small radius over XY plate. And in that slide is 10 centimeters thick. And each slice was fitted with the parabola or a spline to understand what's the minimum. And then the movement of that minimum was fitted with an exponential plus constant. So we get the support term, and considering all the systematics related with the bismuth possible non-uniformity, bismuth is very uniform, actually can be demonstrated. We have 10 to 8 plus minus 1 counts per day per 100 tons. So we have the number for bismuth. So we can put at least an upper limit. And that's what we use in the analysis, or we don't use. Now, a new feature that was introduced in the Borg-Sino analysis is the directional sensitivity, what we called correlated integrated directionality. So the principle is very simple, that if you have a scintillating detector, it also has a Cherenkov-like component. The Cherenkov-like component is much faster. So if you take only the first hits, you actually have a lot of Cherenkov light, which is not uniform. And we can correlate it to the direction to the sun. So on the right, you have the pictures that if we take just the Monte Carlo for uniform background, well, and the real data, they differ quite a lot. And as from this difference, it is possible to derive a component that is correlated to the direction to the sun. Of course, it's an integral approach. We cannot measure the direction for a single event, but integratively, it is possible. And as for the CNO region, it is possible to understand with a PAP bound, of course, that could be obtained from the radiochemical experiment, so an external bound. We can obtain the value for the CNO just from the directionality, and it's around 7.2 counts per day per 100 tons, so more or less the same number that we get from the spectral fit. I'll show the numbers in comparison together a bit later. So, well, the detector response model is modeled both Monte Carlo. We have a very good Monte Carlo, probably one of the best for a liquid scintillator, and an analytical approach, which is quite old, but still it's something that can be used for cross checks. Our likelihood was very simple, but then became not so simple because there are two histograms. There's a radial distribution that is used in order to understand the external components. There's a position reconstruction likelihood, which is used for carbon-11. Then if we use the CID, we of course use the likelihood from there. We can use the pool term for bismuth, etc., etc. There could be other pool terms. So it was a simple likelihood, but then it's not so. So in the very end, we have the fit. It is practically the largest data set that's used for the CNO since the data acquisition is over, and we do have a good fit. And just coming to the numbers, these are the profiles that we are getting for the CNO measurement. So for the full measurement, we have 6.7 plus 1.2 minus 0.8 counts per day per 100 tons, excluding no CNO hypothesis at 8 sigma level, and already we can have some hints about the metallicity. We prefer the high metallicity, as you can see. And also we have a independent from bismuth limit constraint on the CNO coming from directionality, which also has more than 5 sigma no CNO hypothesis rejection. This is probably, so the goal of the Borg-Sino to get the CNO is achieved. So, well, these are basically the conclusion that we have updated the CNO measurement. Now we have a measurement without bismuth constraint, and actually without spectrum. And we have reached more or less, as for the Boroxina, the maximum sensitivity for the CNO. It can be maybe enlarged a little bit more, but these are already very small numbers. Probably this will be the best measurement of the CNO by Boroxina since the detector is no longer existing. Well, just a list of references, and well, thank you for your attention.
Thank you very much. Are there any questions? Comments?
Thank you for amazing talk. So are you still running? I think a few years ago, the news that decommissioning should started, but
September 2021, almost 2 years.
Yes.
So no, we are not running. We would be happy to, because it was a unique detector with unique radio purity that could have measured probably a lot of unique things. But unfortunately, no. The political situation made the detector decommissioned.
Okay, so a few years ago, like maybe in November, they stopped.
September 2021.
They started decommissioning, but then they stopped removing the water and scintillator from the detector. Then they renewed it, right? So there is no water, no scintillator in the detector anymore.
As I know, there is no more scintillator, at least inside the detector, because it was just a direct reaction. No liquid scintillators in the LNGS. So this was related to LVD and the Boroxina. Unfortunately, I haven't visited Gran Sasso myself since 2020, so I'm not aware of the situation very precisely. But as far as I know, there's no scintillator for sure.
Okay, thank you.
Any other questions online? No, nobody. So let's thank the speaker again. And I invite the next speaker, Dr. Wang, who is gonna tell us how Juno detector develops.
Thank you. All right, here I am again. Thanks for the invitation. Honored to present the Juno collaboration and the experiment and its latest status to this audience. I'm from Sun Yat-sen University, representing the collaboration. So Juno is using reactor neutrinos, so that I feel this is proper. And first, the discovery of neutrino and detection of reactor neutrino happens at the same time. The Savannah River experiment, 1956. Beta decay creates reactor neutrinos, and we use the inverse beta decay channel to detect the reactor neutrinos. So far, as I will show, and also has been well known in the field, this is still one of the most powerful ways, most of the precise ways to detect reactor neutrino energy spectrum. And I think this is proper to show it here also. Ponte-Cabo festival is just passed. And we know the neutrino oscillation was first proposed by Ponte-Cabo, and immediately later, not immediately, but a few years later, extended to the three flavor one. So this is the standard neutrino oscillation phenomenology. I won't go through the details. I think two things worth pointing is the amplitude is proportional to the square of sine of double the mixing angle, and the frequency is proportional to the mass square splitting. And this is one of the reasons that for the neutrino mass hierarchy, we need special ways to detect them, because mass eigenstates and flavor eigenstates are not the same eigenstates. And because of oscillation, because of the smallness of the neutrino mass, we have no way to probe the neutrino mass hierarchy except via this oscillation channel. So this is going to be the problem that's being attacked by the Juno collaboration. So the principle actually was pointed out back in 2002. When CETA-13 was not known yet, actually at the time, large or small solar mixing angle was not resolved either. So you can see if the neutrinos, are follow inverted mass hierarchy, it will be the light green line behind this. The two oscillations, the solar oscillation and the atmospheric oscillation, coexist on the same energy spectrum. But if it's the normal mass hierarchy or normal mass ordering, it will be this front solid line. So there's a small shift between two different mass orderings. However, in our experiment, will be only to measure only one. So there's no comparison. So whether you are making a mistake or whether you are fooling yourself, it's quite a tricky question. And also you can see the energy scale or the smallness of those wiggles plays an extreme challenge to your detector. There are other ways to attack this problem. So you can use the matter effect to differentiate different orders. You can also use collective oscillation from supernova if you are lucky to observe one, or you can also constrain this from cosmological data. It's using global analysis. But you can see the cleanest approach is using the reactor neutrinos via the interference between the solar and the atmospheric neutrino oscillation. They coexist on the same spectrum, and as long as you can differentiate those small wiggles, you'll be able to fit your data to identify which mass ordering best fits your data. So this is the effort, this is the principle of this group of people this is the Juno experiment. We are using the Yangjiang reactor power plant and the Taishan power plant in southern China. So this is the globe, and this is Chinese map, and this is where we are, southern China. Worth pointing, the Yangjiang power plant is just like the Diabei power plant, 6 pressurized water reactors. And the Taishan power plant is actually the first European pressure water reactor in the world. It's 4.6 gigawatt of thermal power. Original plan was to build 4 of them, but later the plan was changed back to 2. And you probably heard of the difficulties with the very first one due to some inconvenience, but we can discuss that offline if you want to know more of the details. So besides this eco distance, eco baseline, not far, central detector at the Juno site, we also have a small satellite experiment, Juno Tau, that is, this is small, about 40 meters away from the very first EPR reactor on Taishan campus. So there's also a satellite front or very short baseline reactor experiments in our collaboration. This is the bird view of the site, situated in a small valley, very beautiful surrounding. I hope you have opportunities visiting us. And we have dug a tunnel about 500 meters below the surface, below sea level. The overburden together is close to 700 meters. So in this deep underground lab, we have built the Juno experimental hall. And this is the Juno collaboration. We have 17 countries from 74 institutes, including Moscow State University and Joint Institute of Nuclear Research for nuclear research. And together we have 70 members. And this is the last collaboration meeting back in July, happened about 50 meters away, 50 kilometers away from our Juno experimental site. The first time the second time we got together after pandemic. The first time was close, too close to the opening, so people were still nervous. But this time, we had a big party. Everyone was so happy. Also getting together also for the progresses that I will show. So to identify those small wiggles, you can imagine is highly challenging. So this would be the ideal case. In one case, the interplay between solar and atmospheric oscillations will will generate such a beating oscillation. However, the world is not ideal. If you have a small shift, if you make your delta time square wrong for the atmospheric oscillation, then this beating signal is disappearing. Again, in the real world, there's a statistics. If you have statistical fluctuations, and this is what you are going to see. So it's highly challenging to identify the small wiggles. So in summary, there are 4 challenges for such an experiment: energy resolution to tell the small wiggles, energy scale to make sure you are not fooling yourself, and statistics, to have strong enough of the signal. And then the shift and the reactor distribution are the same thing. If you make a mistake about the baseline, and this baseline is half cycle, half oscillation cycle, then your signals are killing each other from different reactors. So those 4 challenges are the most difficult challenges for such a kind of a experiment. But anyway, we decided to do this, and I will show you how we are attacking each challenges in our design. So to get the statistics sufficiently, we are building a huge detector. This is a 20 kiloton liquid scintillator detector. This is unprecedented in the history. Such a huge liquid scintillator detector. And to tell the wiggles, the resolution, we are reaching 3%. This is basically the solar delta time square, the ratio between the solar delta time square and the atmospheric delta time square. So I will skip the details given the interest of time. So for the detector, to hold 20 kiloton liquid scintillator, we are using acrylic vessel. So step 1, polishing, cleaning, and protecting them, and installation. In this July, we have reached the equator of the reactor. So far, the quality control has been satisfactory, both transparency and the radio purity. To collect sufficient amount of photons, we need to cover the surface with PMTs as much as possible. That's how tight we are packing our PMTs together. Big PMTs, about 3 millimeters apart, about 3 centimeters apart, 25 millimeters apart. And between the big PMTs, we also put in 3-inch small PMTs. So the big PMTs, there are 2 kinds. One is the conventional Hamamatsu one is the Chinese North Night Vision Light, the MCP type. The Hamamatsu one has better time resolution, TTS. The MCP one has a slightly higher quantum efficiency. So they complementarily function in our detector. And this is the installed PMTs. This is a real situation picture. We have installed 4,600 20-inch PMTs and 3,600 3-inch PMTs as of end of June. Together, we have 20,000 20-inch PMTs. So we are about 20% done. To tell the energy scale right, we have 4 complementary calibration systems using different strategies. There's an automatic calibration unit. There's a string-like calibration unit, cable loop system. We have also guide tubes around the detector. We also have a small submarine inside the detector, remotely operate under liquid scintillator vehicles. It's really fancy to carry the radiation sources around the detector. So we are confident with some simulation to reach the energy scale less than 1%. This is required in order not to make a mistake or not to fool yourself. And the liquid signature system, we are collaborating. Actually, Barcino collaborators from Italy are on the collaboration. This is their contribution. Our previous colleague already told us how clean Barcino is, and we are confident we can produce high quality, high light yield, and high purity liquid scintillator. So we are going to start filling next summer. So all those hardware designs will eventually give us such a signal. This is the signal observed inside the central detector using the PDG parameters, considering solar oscillation and atmospheric oscillation. So I will skip the details, basically around 50 events per day and about 10% background. With those kind of signals, we can reach about 3 sigma level with 6 years of running for the mass ordering identification. And with this opportunity, this large detector, actually we can reach sub% precision for 3 oscillation parameters. They are atmospheric dot-time square, solar oscillation dot-time square, solar mixing angle. And of course, for CD13, we have some kind of sensitivity, but the best one is the current short baseline experiments, Diabe, Reno, and double show. Of course, Diabe dominates the statistics. And I like to point out those precisions and those parameters can only be probed in coming years, in the foreseeable coming years by Juno. So Juno only, especially the solar oscillation sector. Okay, so reactor neutrinos are almost perfect. I mean, we are very thankful for reactor neutrinos, the discovery of a neutrino, the measurement of CD13, and the future identification of mass hierarchy. But we know reactor neutrinos are not ideal. There's this so-called RAA, and also the discrepancy at the around 5 MeV location. We call the bump. And this is due to the complication of the reactor physics inside a reactor, because there are hundreds, thousands, if not 10,000 fission products, and they are together, they are giving us this, okay, thank you, this reactor anti-neutrino spectrum. So you can imagine it's really easy to mess up something. So in order to have those 2 anomalies resolved, we also designed this Juno Tau satellite detector, or satellite experiment, as I mentioned earlier. This is about 40 meters away from the world's first European pressure water reactor. And the goal is to reach resolution. This is also unprecedented sub 2% level. So based on simulation and the design, our resolution will be 1.5% at 1 MeV. The key to reach this is one is to have high light yield liquid scintillator, and 2 is to collect all the photons emitted by those liquid scintillator. There's not much space in liquid scintillator anymore, but there is space in collecting the light. So we are using silicon PM to cover the whole surface of this small ball. Those silicon PMs are offered, actually contributed by Joint Institute for Nuclear Research. And my group is contributing for the top video tracker, and the local group from Moscow State University is contributing part of the calibration system in this detector. And this is the one-to-one prototype that is being built in Beijing. This is a high purity copper vessel to provide low temperature liquid scintillator and the lower radio, the good radio purity. So you may ask whether tau can help with boosting the sensitivity to mass ordering. It can contribute a little bit, but not too much. The purpose of Juno tau is to resolve the reactor neutrino anomaly and the bump to give us the best understanding of reactor neutrinos. It can help a little bit if you read the curves. So just show you some exciting pictures. Juno is currently in a very exciting phase. You see we are building the mechanical structure step by step. And at the same time, we are welding or bonding the acrylic vessels together from top down. So this is where we are. This is what you see inside that underground experimental hall. It's an amazing structure, 10-story high. So let me summarize. Reactor neutrino has been indispensable, irreplaceable in neutrino physics, and many contributions. And Juno is using two oscillations on the same spectrum, trying to identify the neutrino mass ordering. And this is the only experiment in the world using reactor neutrinos. Juno will also make precision measurements for 3 of the oscillation parameters. And this is the only experiment doing this in the foreseeable future. And Juno construction has entered its final stage, and we are expecting data next year. So thanks for your attention.
Thank you very much. Questions?
For a review of Juno and prospects of this experiment. Okay, I have mentioned that when you compare the expected new results on these oscillation parameters that will be accessible with Juno, you compare these results with those that published in peer particle data group 2020, but there is a 22 plus the upgrade of this year. Other changes or no?
No, not much. The precision, you see, the progress or the improvement for CD13 is almost frozen because database stopped taking data. Also, the systematic uncertainties and the statistical uncertainties are almost equal. So there's no point to take further data. And nobody has touched the solar mixing angles, the solar oscillation parameters for quite a while already. And atmospheric dot m square has been improving slowly from year to year, but not much, still at this level. So, yeah.
Thank you for a nice talk. Is there any chance you can use atmospheric neutrinos for measurement of oscillation parameters?
Yes, we do have. Let me see whether I have that picture. Probably I don't. Wow, this is the multi-fix. This is a diagram. The atmospheric neutrinos, because we are only reaching 3 sigma nominally, if we only use the simplest approach. So we are trying to get more statistics or contribution here and there. Atmospheric neutrino definitely will contribute considerably. We are trying to understand how we can reconstruct those energy and direction better. Also identifying mu plus and mu minus in our detector. They will all help. So the contribution to mass ordering won't be zero. So for neutrino oscillation physics. Also, I'm sure neutrinos will be extremely useful for some kind of new frontiers like Earth tomography and even CP evaluation if we could do better job in identifying those events. So that's.
Thank you.
Yeah, thank you.
Thanks a lot for your nice presentation. Are there any prospects for Juno experiment somehow to improve or to make better bounds on dark matter searches for different cases?
we only capable of trying to study the indirect searches, and that's we
So
know
you didn't
is-
make any modeling up to now, or what?
we are not the collaboration. I mean, the main job is to run the experiment. Of course, their phenomenology colleagues, you know, like Alex and people in the field are working on that. But as far as I'm aware of, I think we have not invented new models, but we have done new analysis using existing phenomenological models to identify, to see how well we can do for each of kind of models. So indirect only.
Yes,
just independent.
but you do not have numbers up to now.
I don't have numbers offhand. Sorry, yeah, but you can check our yellow book, Juno physics report. We have quite a few nominal studies for indirect dark matter searches. Yeah. Yes.
I know that Juno has plans to study supernova neutrinos. So suppose that a core collapsing supernova explodes in our galaxy. What is the energy threshold for such a part?
The energy threshold, well, because for the we also have a solar boron 8 neutrino, like baryogenesis, a goal. So the threshold won't be an issue. The typical energy we know is dozens, 20, 30 MeV. So that won't be an issue. Our detector linearity is quite good to GeV level. So we don't worry about the energy threshold. We worry about the pileup. So we do have a multi-messenger running mode. Suppose there's a galaxy, there's a supernova bursting in our galaxy, and that would be the thing we worry the most, whether we could record all the events. So we do have that trigger that is being designed. So, and also we are communicating with SNEWS to join the global warning network. So if that answers your question, I'm sure. Thank you.
Let me invite the last speaker, Alexander Dolgov, who is gonna tell us something interesting about primordial black holes.
Thank you. And my subject is quite different from all the rest presented today. I will talk about problems which were found in observations of James Webb Space Telescope and Hubble Space Telescope, and the way how they can be solved by assumption suggested many years ago, 30 years practically, in our old paper, and we also there are also some new data and the further development of this approach. What should I? Oh, something wrong. Oh, or I did something incorrect. Okay, so I start from the end that there are certain arguments, observational arguments, in favor of these ideas. First of all, that well, I already said that James Webb and Hubble telescopes created strong doubts of the validity of the standard cosmological model, and it was conjectured 30 years ago that galaxy formation and quasars and many other cosmic structures are really seeded by primordial black holes, so that it was quite opposite to the standard mechanism of formation. I will talk about that later, and this idea about seeding cosmic structures by primordial black holes was somewhat reluctantly taken by the community, by the establishment, but during last year there are several papers where the same thing is repeated. In a sense, it is a rediscovery of our old result. Not completely complete coincidence, but at least some agreement, I would say. So there are some data which is very well tested by, I would say, experiment. Fortunately, we cannot do experiments over the whole universe, so it's better to say by observations. First of all, that the model predicted a very simple form of mass spectrum of primordial black holes in log normal spectrum. I will present corresponding expression, and this is this indeed very well agree with observational data. Next thing is absolutely crazy statement that galaxy, maybe our galaxy Milky Way, may be abundantly populated by antimatter objects. It could be well, there are a lot of data, and for example, very many positrons observed, though there are maybe different explanation of that. But another thing, that anti-nuclei, which is practically impossible explained by any other way, except for assuming that antimatter indeed lives in the galaxy. And relatively recent work, possibly even anti-stars are observed in the galaxy. I say possibly, but okay, it's all taken all together. Maybe we should delete this possibly, all these things. Next thing, and I already repeated, all controversial data, controversial, I mean, with the standard cosmology observed by James Webb telescope, in fact, also by Hubble telescope, that the economical and simple solution is that all these objects are seeded by primordial black holes. And another thing very recent, that there are distortion of pulsar timing, which is possibly created by unexpectedly large amount of black hole binaries. Very good. So the question is if this crisis in cosmology real, and I said probably not. And if we agree that there are very strange objects from the point of view of traditional astrophysicists, namely primordial black holes, and it was our two papers with Joe Silk, and later on developed in our paper with Masahiro Kawasaki and Nina Kivishvili. It is interesting that in these papers were even in the title mentioned dark matter made of black holes and also about cosmic antimatter. Okay, so I already said that we suggested inverted mechanism of galaxy formation, namely first black hole is formed and attracted matter around to create galaxy, and standard way is that we have galaxy with excess of matter at the center, and there is accretion of matter created to leading to creation of very massive black holes, but standard accretion mechanism is short by approximately order of magnitude, even in contemporary galaxies, to create such huge black holes living in galactic centers. And if we speak about universe, which was very young, at redshift of order 10, at that time, at that moment, corresponding time was about factor 20, 30 shorter than the universe age today. Okay, so there are a few pictures. It is James Webb and Hubble telescope. Then there are characteristic feature of these instruments, namely Hubble telescope is very close, rotate practically around the Earth, very close to that, and James Webb is at a distance of what is about million kilometer, 1.5, and mirror is approximately 3 times larger, slightly less than that, and it's so sensitivity is factor 40 is better. And what is important that Hubble telescope works in visible light, wavelength optical, and what is written here, blue, and some ultraviolet. And there are also some possibility to measure in micron range. As for James Webb, it works only in micron range, and that's explain, well, at least better sensitivity, and also some problems related to well, how to say, confined, restricted region of wavelengths. So there are some pictures. If you look here, how could I use it as a pointer? This one, okay. Okay, so there are, this data is data from James Webb, and this is the same object accidentally, by some lucky chance, discovered by Hubble Space Telescope, and these are the same object with the same redshift. So there is confirmation of the agreement between two different instruments. Okay, now there is some data. What is written here, it is data from James Webb, and for example, these are theoretical predictions of lambda CDM cosmology, and since this is a logarithmic scale, you see that disagreement is indeed quite huge. Okay, now there was for a long time, or for a few months, some skepticism about James Webb data, because spectrum of the objects at that time was not known, and starting approximately from February of this year, there is accumulation of multiple data when excellent determination of the spectrum, with only one case when object which was prescribed by James Webb to very high redshift happened to have much smaller redshift. There are several examples. I simply quoted several papers with different wavelengths and different papers. Okay, there is not only galaxies, but quasars or active galactic nuclei, whatever, observed also by ALMA, which is well, also very powerful instrument. It allows to measure the spectrum and proceed to very high redshift. There is what is written at this title of this talk, that or in abstract, absolutely impossible galaxies, 6 galaxies, very well developed, were observed. It is like grown up, instead of small children, there are grown up adults, with which they say, science says that it is impossible to create such developed objects in such short time, and they say that maybe these objects are supermassive black holes of the kind never seen before. I don't know how to decipher it. Probably they mean something like primordial black hole. So the statement very provocative that such objects, such fixed objects may be black holes of the kind which we have seen. Okay, there are first paper which return to idea of seeding galaxy formation by black holes was by Leo and Brom in a year ago. It was practically 1 year ago, but by now there are even more and more accurate papers. There is paper by Bogdan and others. They say that their observations suggest that galaxies are seeded by black holes. The origin of these black holes rather shaky. They say that there could be direct collapse, but it is not so easy to make in this way black hole because gas is heated. There could be not to be very many heavy elements. So as I talked to real experts, my colleague, and they say that it is almost impossible. So to create it by direct collapse. Okay, let's. There are a few more papers of seeding of different authors. So I've simply collected how many? 3 of them. Okay, now there are another interesting things observed very recently. 2 kind of very old stars in the galaxy. They say that there are objects, so primordial stars in the galaxy. The age of those stars estimated by the standard method is approximately equal to the universe age. So there are quite surprised. Our galaxy has aged, roughly speaking, 5 or maybe more, 6, 7, maybe billion years, but there are stars which has aged 14 billion years, and another so-called pristine stars, another group, which are also very well, untouched by any kind of development. So it's indeed very interesting. There is also something that I wanted to mention, that even prior to James Webb, there existed problems found by Hubble Space Telescope, and it was described in my review in physics, Russian, вот physics успехи физических наук, and there is indeed big collection of the data which didn't fit to the standard cosmological model. Опа, хорошо, I have to rush. So there is maybe just several things mysterious observed in the galaxy. Now, there are 3 types of formation of black holes, so-called astrophysical. So they are normal black holes. The star exhausted its nuclear fuel and collapse with sufficiently large mass, a black hole is formed. Another is supermassive black holes observed practically in all where observation is possible. In any large galaxies, such black holes are observed, but in addition, there are black holes, supermassive black holes, observed almost in empty space. Probably they are wandering black holes, but there are too many of them. Okay, now primordial black holes, as I said, it was pioneered in paper by Zeldovich and Novikov, then elaborated by Hawking and also developed by Carr and Hawking, just to the right. Another thing that typical for our model, that black holes were formed in the process of inflation, and it allows to make primordial black holes with huge masses of up to billion solar masses almost. Old papers without inflation allowed to make very, very light black holes. Oh, there is classification, I would say conventional, that black holes with masses from million to billion solar mass called supermassive, intermediate mass black holes. Okay, that's relatively light, and there are plenty of them. Nobody expected it. Now there are so many, and there are even black holes, maybe a fraction of solar mass. I skip that. Now, a few words about black holes in contemporary universe. This example of log normal mass spectrum. Here it is, and theoretically we may predict the value of central mass. It's the order of 10 solar masses, and experiment. Let me go further away. That the spectrum of chirp mass of gravitational waves seen in coalescence of black hole pairs is very well described by the by the log normal form. It is best fit. By the way, the value of central mass is about 17 solar mass, which nicely fits our prediction. And the form is like that. And another thing, it is like LIGO data, and you see that a few models of astrophysical black holes are not so good. Okay, let's go further. It's some new analysis made by Pasnov and Mitichkin, and there is somewhat maybe some contradiction about black hole, about black dark matter made of black holes. There are strong limits which are presented here. We need to make, please give me 1 minute more. Okay, so we need black holes in this region. You see that they are forbidden, but according to Carr, private conversation, and he mentioned in his talk that it is all these bounds are model dependent. They are also found by for monochromatic mass spectrum, and there are some criticism of that, and especially what I very recent one, there was paper by Rubin and Tal that formation of black holes, well, primordial black holes may form clusters, and in these clusters, according to the papers, recent analysis by Yaroshenko and Zvisenko, based on Japanese people, there is allowed to have 100% of cosmological dark matter made from black holes. Now, what is interesting distortion of pulsar timing, that there is existence of large number of primordial black holes, curved space, and nice clock is pulsars are distorted, and it is observed. To this end, now I think I could skip that. That's interesting. Maybe antimatter history. First person who started to study was Konstantinov. Now there is an institute called after him in St. Petersburg, and he was looking for comets in our Milky Way. Zildovich, who was in a very good relations with him, said, good physicist and doing some working on some garbage. So maybe it was not garbage, and it's maybe possible. And there's antimatter was studied, I think, pioneering papers by Floyd Staker, and also some reviews on that. Father of antimatter is supposed to be Paul Dirac, and he said that there could be stars and anti-stars. And in fact, it was like something funny, maybe. Another British physicist, Arthur Schuster many years before suggested that together with electron there could be positron, antinuclei, and whatever maybe. And he said that matter and antimatter gravitationally repulsive. Well, that's wrong, but that matter and antimatter can annihilate, producing vast energy. That's, I don't know how he guessed it. Completely correct thing was now there was some limits of our early papers that antimatter in the Milky Way is allowed, and then there was some data on positrons, on anti-helium, and some other anti-deuterium, which may be produced secondary way. And let's go away. And then there is secondary production. This was estimated in this work, and they are practically not allowed. There are some. Okay, I'll go next. That there was anti-stars probably observed by this group, Deeper-Q, Thibaldo, and von Balmus, and there was also our paper studying with Bonder and many other that this French group observed excess of 500 MeV radiations from 14 stars. But that's an interesting idea that proton antiproton do not have head-on collision, but they form atoms like positronium, and they jump from level to level, and there are very well defined atomic levels in K region which can be observed. There was another paper very recently where we studied some other implication of this idea, and probably the most natural mechanism of formation of this anti-helium and the other anti-nuclei is antimatter. Now, I think I will skip theory, which was published in many other ways. It is more or less natural model of interaction of scalar baryon, which existed in supersymmetric models, with inflaton field, which is written here, and then there is anti-creation mechanism, and I conclude, looking at the angry face of the chairman, that primordial black holes save lambda CDM cosmology and explains the origin of galactic antimatter. Please louder. Oh.
The content of this talk, excuse me, to the theoretical subjects. How it is possible? How you may explain that it is very beautiful and complicated subjects. The simple equations like x minus gamma log m divided by m star squared do appear. What is the theoretical basis under this simplification?
Oh, I didn't get.
Ну, у вас там в формуле, наоборот, с уважением, очень все красиво, очень все интересно, просто теоретически вы заканчиваете. У вас очень простое выражение экспонента минус,
сейчас я
минус
скажу.
гамма
Тогда
логарифм
немножко
m
назад
square
вернуться.
делить на m квадрат. Ну, там же должно быть какая-то теория за этим, и она наверняка, вы наверняка об этом знаете.
А как мне назад-то пройти? How I can go back? Теория состоит в следующем, что, sorry, we introduced new interaction of scalar baryon with the inflaton field. Here on the right, and when phi capital close to phi1, then effective mass of scalar baryon becomes negative, and this state is unstable and goes far from the equilibrium, and it means that we acquire large baryonic number. This is natural interaction of two scalar bosons. It is simply renormalizable interaction, quadratic, cubic, and quartic terms. Okay, so then phi plus through phi 1, then gate and flow, chi return to equilibrium starting to rotate on the way. Rotation in complex chi plane means baryonic number. It could rotate clockwise or anti-clockwise, depending upon relative direction of quarks and quadratic potentials. Okay, so we naturally expect that antimatter can be produced, such objects may be produced even in the galaxy. And then we solve diffusion equation. We solved diffusion equation, which was suggested by A.Starobinsky about fluctuation behavior of this scalar field in de Sitter space masses. There is so-called masses instability of scalar fields. Sorry, quantum instability of scalar field in the de Sitter in exponentially expanding universe. Okay, and then it was rather technical. It can be shown that indeed the spectrum is very, very simple. This is log normal. And there are a few pages of calculations, which we did with Joe Silk, and then we elaborated with Kawasaki and Kevrishvili. So it was obtained, and we can find central mass because we have bubbles with large baryonic number with massless quark. So there is universe like Swiss cheese upside down. There are not holes, but bubbles with high baryonic density. At the moment when while quarks are massless, there is density contrast is zero. We go down to temperatures of around 100 MeV. And at that moment, all these quarks suddenly became protons and neutrons nucleons. And so density contrast is huge. And so in this way, mostly black holes are formed. And central mass is equal to mass of horizon at the QCD phase transition. Okay. Okay.